determining empirical formulas using combustion analysis. So combustion is an awfully useful thing to do. It really was the go-to experiment that you'd use in the 19th century. What's in here? I don't know. Let's burn it and find out. So it was really useful for virtually, a lot of the stuff that Dalton did involved burning gases, burning liquid, and figuring out what came out of that. So we talked a little bit about in the previous chapter about determining finding out how much of each element was in a compound and using that to figure its molecular formula. But how did you actually figure out how much of an element there is? So combustion analysis is a good way to do it. So for example, you can determine the amount of CH and oxygen content in a compound by examining the amount of CO2 and H2O combustion products formed. So this is used routinely for determining empirical formula of unknown organic compounds because a typical clean combustion reaction of organic compounds is something of the form CXHYOZ. We don't know what X, Y, and Z are, and that will produce a certain amount of oxygen, carbon, and H2O. And you know that all of the carbon, however much carbon dioxide you get out, all of that carbon came from the carbon in it. So you collect the amount of CO2, figure out how much carbon was in that, and then you know how much carbon was in the original compound. Also, you burn the H, you're burning this all in pure H2O. That H will give you collect the water that comes out, and the H that's in the water, you know that all of that H in the water came from the H in the carbon moiety. Now, the one thing that the carbon compound that you start out with, the one thing left over is like, how do you figure out how much O there was? Because in reactor, you combine it with oxygen, and what do you do then? Because you measure the amount of oxygen that came out, but you don't know how much oxygen went in to begin with. Well, the key is, if it does only contain C, H, and O, then you just, the amount of mass left over in oxygen is what's ever left. So because you know the total amount that went in, you know the mass of carbon, you know the mass of hydrogen, therefore you know the mass of oxygen that was originally in it as well. So it could be used to determine nitrogen content in organic compounds as well, because you determine the mass of NO and NO2 form. Usually you get both NO and NO2, but if you sum all of those, that gives you all the nitrogen as well. And if you accumulate your CO2, your H2O, your NO, and your N2, if you've got all of that, then you can figure out how much oxygen was left in there as well. So you could actually keep on doing this along that process. So that's the procedure. That's the idea. What is the procedure by which you carry it out? So as that's. So just you can see that equation at the bottom. You collect the carbon dioxide, the water, the nitrous oxide, the nitrogen dioxide, and then that will give you what the molecular formula is. Okay, so yes, we get the idea. How do we carry it out? Okay, so we have 4.50 grams of an unknown organic compound containing only carbon, hydrogen, and oxygen. We burn it, we get 10.24 grams of carbon dioxide, 4.16 grams of H2O. What's the empirical formula of this organic compound? We can only figure out the empirical formula here because it's just going to give us the ratios. It's not going to give us the total amount. We have to use other ways to find the total amount that's in there. Okay, so let's dive in. So what we want to be doing is converting from grams to moles. So we've got 10.24 grams of CO2 reacting with 1 mole. We have our conversion factor. And again, I'm not going to actually calculate the molar mass of CO2 or H2O here, but you'll do it. Then you'll get that the molar mass, that is one ugly CO2. 44.01 grams of CO2. The grams of CO2 cancel out. And now, first of all, what we're trying to figure out the mass of, we're trying to figure out the moles of carbon, not the moles of carbon dioxide. So we see that there's, for 1 mole of CO2, there's 1 mole of C, cancels, and we get 0.232 moles of C. You might think, well, every carbon has 1 carbon dioxide. Yeah, it's pretty straightforward. Gotta remember, each molecule of carbon dioxide has 1 atom of carbon. Why do we need a conversion factor there? Just wait. Okay, 4.19 grams H2O, same process, figuring out how much hydrogen was in the water. 18.02 grams H2O per 1 mole of H2O. And we now, each 1 mole of H2O actually has 2 moles of H. So if you're counting up your moles of H, you got to remember there's 2 per water molecule. Grams of water cancel, moles of H2O cancel. I'm going to get 0.464 moles of H. If you forgot that factor of 2 moles of H per H2O, you would severely undercount your H and get the wrong empirical formula. All right, so now we need the number of moles of O. So what we got to do is go back, figure out what the mass of the C is, the mass of the H is. The mass of C is going to be 12.01 grams of C per mole of C times 0.232 moles of carbon. That gives us 2.79 grams of carbon. And our mass of H, we have 1.008 grams of H per 1 mole of H. Pen was tired. Okay, now it woke up. 0.464 moles of H. That gives us 0.468 grams of H. So 4.50 minus 2.79 minus 0.468 gives us 1.24 grams of oxygen. So 1.24 grams of oxygen, we need to figure out how many moles of oxygen that is. Grams O, that gives us 0.0776 moles of O. Now clearly in a single molecule of this organic compound, it doesn't have 0.232 moles of carbon or 0.464 moles of H. That's just the ratio. So we need to divide this to see if we can get some low number or so. Let's guess that there's less oxygen. So we have C over O, the number of C, number of O. Why oxygen? Because that's the lowest number. That's usually the best one to go with. There's more carbon and oxygen, so let's divide by the lower one so that we get larger numbers in the things that there's more of. So that gives 232 mole C per 0.0776 mole O. 2.99 is the ratio of carbon to oxygen. Number of H, number of O is 0.464 moles H. It's O776. Mole O equals 5.98 moles. So this is something you'll generally see. You're never going to be making these. Measurements entirely accurately. There's always going to be, some measure of non-total yield. So you're frequently going to see numbers that are not exactly integers. They'll almost never be exactly integers. But if they're this close to 3, you can probably say, yeah, I'm pretty sure that that really is 3, that really is 6. And so there are 3 times as many carbons as oxygens, and there are 6 times as many hydrogens as oxygens, which would mean that this would be, as an empirical formula, C3H6O. That does not mean in this compound there are exactly 3 carbons and exactly 6 hydrogens and exactly 1 oxygen. It just means that the ratio is 3 to 6 to 1. And that is how you do a combustion analysis in order to figure out the empirical formula.